that I just mentioned. So, all right, so welcome back. We are now in the end of the 8th week. I think this is lecture number 15. And we are now hopefully going to finish chapter 18 today and possibly even start another chapter. We're dealing with the power of a statistical test of significance. So let's remind ourselves what goes on in a statistical test. So again, the main ideas of a statistical test are we start with a belief called the null hypothesis, H naught. Start with a belief. We question that belief and hypothesize an alternative, or hypothesize a competing belief called the alternative hypothesis. Either HA or H1. And then we take a sample and we use the results of the sample to either reject H naught or not reject H naught. Okay, that's the idea of a hypothesis test. Those are the four main ideas of a hypothesis test. So as an example, suppose we have a hypothesis test where somebody claims the average of some distribution should be 0, and you come along and you say, no, I believe that the average is greater than 0. So if I look at a distribution, I always make my drawing of the distribution, my original distribution is drawn under the assumption the null hypothesis is true. Under the assumption that the null hypothesis is true. Under that assumption, what is the mean of this distribution?
0.
0. Now, if I believe that the mean is greater than 0, I would need some evidence to support that and to reject the null hypothesis. I would take a sample and I would presumably look at the sample mean and I would say, hey, my sample mean is this. I'm going to reject your claim that the null hypothesis is 0. What are some potential values of my sample mean that might make me reject the claim that the null hypothesis is 0 in this case? Would a sample mean of 1200 make me reject the claim that it's equal to 0? If I got a really, really big sample mean, would you come along and say, yeah, maybe 0 wasn't right to begin with. Maybe it's actually greater than 0 like you were claiming. Is that a reasonable conclusion based upon the sample? Anyone? Hello? If you get a large positive sample mean, would that give evidence to support the alternative that the mean is really greater than 0? I don't know if anyone's writing in chat because I have my ebook up. Oh, I got to keep bouncing back and forth. Oh, I have 8 people. Oh, wow. Sorry. Sorry, everyone. I didn't realize you guys were commenting. I didn't see any of that because I had my ebook open. But I have a lot of yeses. And I have a no. I have one no. Why do you say no in that regard? The answer is yes, by the way. Okay, if the belief is that it's 0 and I take a sample and I get a huge positive number, that's really lending evidence to support the claim that maybe it was greater than 0 all along. So Cynthia, you said no, and I'm wondering what the logic behind that is.
I understood what like you were asking wrong, but
Okay, so you're with me then?
Yeah.
Okay. Now, if I got a sample mean of negative huge number, like negative 1,000, would that support the claim that the mean is greater than 0? Would a negative sample mean support the claim that the mean is greater than 0? No, which means the only location on this curve where I might get data to support the alternative would be to the far right. Big values, big positive values. This is the critical region. It's the section of my distribution where values might make me reject the null hypothesis, also called the rejection region for that same reason. Does that make sense? Now, if I had another example, H naught mu is equal to 0, H1 mu is less than 0. Okay, if I gave another situation where my alternative hypothesis was that the mean is less than 0, where would my rejection region be in that example? Where would values have to fall to make me claim that the null hypothesis is wrong and that I'm going to reject it? That will be far to the left. And what if, as the following example, what if I had a null hypothesis where mu is 0 and my alternative is that mu is just not 0? I don't care if it's smaller or bigger. I just don't think you're right. I just don't think it's 0. Where would values have to fall now for me to reject the null hypothesis? The left or the right? So in that case, the null hypothesis, the rejection region would be in the far left, and it would also be in the far right. Make sense? You all with me so far? Okay. Now, going back to the book. Okay. Suppose you have the following situation. Suppose you have some null hypothesis, right? Suppose you have an H naught where some parameter has some value. I don't know if the book, I don't know, suppose, so let's do an example. I'm gonna do this example from the book. So suppose we have a null hypothesis where mu is equal to 0. And the alternative is that mu is greater than 0. And we're given a few pieces of information here. We're told that sigma is 1 because we need to know sigma. And we have a significance level of 5%. And we have a sample size of 10. So first, what does it mean for alpha to be 5%? What does that mean the significance level is 5%? What does that mean in the context of this problem that the significance level is 5%?
That the p-value is less than 0.5.
Not 0.5. 0.5 is 50%.
Oh, 0.05. I'm sorry.
0.05. Okay, if your p-value is less than 0.05, if your p-value is less than the significance level, that's when we reject the null hypothesis. So the alpha in this case, the significance level, is how small your p-value has to be in order to reach the point where we reject the null hypothesis. Okay. Now, in this example, I'm claiming as my alternative that mu is greater than 0. But I'm not specifying what mu is. I'm not saying, no, mu is not 0. mu is 0.3. I'm not claiming a specific alternative. I'm just giving you a range. I'm saying, I don't know what it is, but it's not 0. It's greater than 0. But what if I provide a specific alternative? Say mu is equal to 0.8. What if I say, I think, or not that I think, my claim is that mu is greater than 0, and I'm going to go one step further and claim that really it's equal to 0.8. So the power of a test against a specific alternative. The power of the test against a specific alternative is what? It's the probability. The test will reject the null hypothesis when the specific alternative is true. Okay, the power of a test for a specific alternative is the probability that the test will reject the null hypothesis at that specific, if that specific alternative is true. So let's think about this in the context of this problem. If the null hypothesis is true, all right, if the null hypothesis is true, what is at the center of this normal curve? What value is right at the center? If the null hypothesis is true, what value is right at the center?
0.
0. And where would I have to get values to make me reject the null hypothesis?
The right.
The right. But in particular, how far to the right would my z-score have to be for me to reject the null hypothesis? I would have to be past that 5% to the right mark, right? Because that's my alpha, correct? Well, what z-score has me 5% to the right? What is this z-score? What's the value of that z-score?
From 0.645.
1.645. If I'm past 1.645, I am at the point where I am in the far right 5%. I did that on my calculator, by the way, or whoever contributed. I'm not sure who that was, but I'm at the cutoff of the far right 5%. Now, what if the alternative is really true? What if the mean is really 0.8? Where should my bell curve be centered if the mean is really at 0.8? Because right now I'm centering it at 0. So where should it be centered if the mean is really 0.8?
At 0.8.
At 0.8, which is about halfway in between these numbers. So my bell curve in that case should really look more like this. Agreed? Yes? But just because I'm changing where the center is, doesn't make me change what my cutoff is. I'm still going to reject the null hypothesis if I get anything above a 1.645, because remember, I don't know what's true. I don't know that mu is 0.8. I don't know anything. I'm just working under the assumption that mu is 0. So I've determined that my cutoff is 1.645, which means anywhere after 1.645, I'm going to reject the null hypothesis. Do you agree? Yes, no, maybe so. So the power of the test is the probability that I get a value greater than 1.645 under the assumption that mu is really equal to 0.8. Okay, the probability that z is greater than 1.645, given that mu is really equal to 0.8. This is the power of the test when mu is equal to 0.8. And every mu will get a different value for the power of the test. So there's not one power. It's always against a specific alternative. And I looked at the syllabus and it was very clear that for this class, power should only be conceptual and not mathematical. So rather than going in detailed into a problem that might take 20 minutes, we're not going to do that. We're just going to keep it conceptual. The power of the test against an alternative is the likelihood of rejecting the null hypothesis if that alternative was really true. And we're just going to leave it at that. So are there any questions conceptually with what we just did?
How did you get 1.645?
1.645 is the 5% cutoff. Because remember, alpha was 0.05, right?
Yeah.
So if alpha is 0.05, that means if I get a result that has a less than 5% chance of occurring, that's when I'm going to reject the null hypothesis. Well, less than 5% means it's on the far right 5%. So I went to my calculator and I plugged in what value cuts off 5%, and my calculator gave me 1.645.
Okay.
Okay. And by the way, I've very, very infrequently ever seen them ask about power. Maybe one question max for like a point, like a multiple choice type thing, as opposed to a major calculation. But when I teach Math 341, we spend a lot of time on power. It's a lot of fun. Of course, fun being relative. So now let's consider the following. I'm going to make a box here of 4 cells, 4 squares or rectangles, whatever. Now I'm going to label the rows as follows. That's not straight. That's still not straight. Okay. I'm going to label the rows as follows. H0 is true. H0 is false. Reject H0. Do not reject H0. Now, 2 of these boxes are you making the good call? And 2 of these boxes are you making a bad call? Which 2 are a good call on your part?
The bottom left.
I'm sorry?
Is it the bottom left? And
The
the
bottom
top right?
left and the top right. Well, let's think about it. If the null hypothesis is false, should we reject it? Yes, that's a good call. And if the null hypothesis is true, should we reject it? No, that's a good call. Those are both great calls. Because we don't know if it's true or false, so we'll never know if we made a good call or not. But conceptually, rejecting it when it's false and not rejecting it when it's not false are good things to do. What about rejecting the null hypothesis when it's true? Is that a good move? No, that's a horrible move. We call it a type 1 error. A type 1 error is the probability of rejecting the null hypothesis when it is true. You can also not reject the null hypothesis when it's false. That's also an error, but we're not going to call it a type 1 error. Can anyone guess? And this might be very tough, but I'm gonna go on a limb and think that at least one of you can get this right. Can anyone guess what we call the error when you don't reject the null hypothesis, but you should have because it's false? Anyone guess what we call that? It's tough, but I have faith in some of you. Hey, we got it. It's a type 2 error. Way to go. And Cynthia even used Roman numerals. So, the other ones like type 2, nobody uses numerical Latin numbers. Roman numerals are the way to go. Type 1 error, type 2 error. You ever notice that? If you use like Roman numerals, it's like considered more sophisticated. Like movies, like, you have like, Rocky 2, it's in Roman numerals, or this 3 or this 4, but like, less classy movies use numbers like 2.5, or, something like that. Anyways, and Alexis, wow, okay, we'll have to go to English class and work on your spelling, but other than that, it was great. Unless that's like a different language, error. That's like a more fancy way of saying it. I actually kind of like it. A type 2 error. I like it. Okay. Anyways, Mariah, are you okay? Hold on, I have a couple people who arrived, huh? I have a couple people who told me that they're late, so let me just update them. And Flower, you were here also. Wait, Flower, I had you, or did I? Joseph Ailman, Michael Arrington, Erilee, Andy, Alondra. Yeah, Flower, I had you the whole time. I don't know. Leanne, Sungjan, and Estrella and Crystal. Have any of you been here? Yeah, okay. So, excuse me. All right. So we have type 1 errors, and then we have type 2 errors. In general, which of these two types of errors would you say is a worse type of error? If you had to make an error, which of these two would be a worse type of error? So Cynthia, you say type 2. I'm curious why you say that. It's not that it's wrong or right. I'm not trying to insinuate one way or the other. And Mary, you say type 1. But I'm just curious why each of you claims the way you do. Oh, now it's like 3-1. I'm thinking like a pregnancy test. So I've never been pregnant, being positive, but it says negative. Being positive, you have to help me out here. What are you talking about?
Wouldn't a type 2 error be if you're pregnant and you take the test and it shows you're negative, but you're really positive?
So you're assuming then that your null hypothesis is that you are pregnant or that you're not pregnant? What's your null hypothesis there? You've been not pregnant your whole life, right? So the null hypothesis will be that you're not pregnant, correct?
Oh yeah, so that's a type 2 error actually.
Well, if you're really not pregnant, but it says, sorry, if you
I have the idea, I don't know which one it is.
If you really are pregnant, but the null hypothesis is false, that will be a type 2 error, correct? What you just said would be a type 2 error. But
Okay, I changed my answer.
okay, so you're going to 1 then.
I'm going back. I'm going to 2.
Okay, you're going to go to 2. So now it's 2-2. Anyone else break the tie? What's worse, type 1? By the way, just so you know, what you just said is a very specific example. And there's always going to be exceptions to the general rule depending on the scenario. But as a general rule, type 1 errors are worse. And the reason why is as follows. Suppose, I'll give you an example. Suppose you are, you're the manager of some factory. You're making some widget, some device, and you have all your machines that are calibrated to make this device, and there's specifications because these things that you're making are going to have to fit into some larger thing that you're going to sell to people. And if it's not the right size, it's not going to fit, and all these bad things are going to happen. So what do? You want to make sure that it's calibrated correctly. So you take a sample and you test it. Now, the null hypothesis is that the size is correct because it's been correct up until now. If the null hypothesis is really wrong, but the test, but you make an error and you think that, and you don't reject the null hypothesis, what would you do? If you came to the conclusion that you do not reject the null hypothesis, you'd go about your day like everything's fine. Okay? You don't got to retrain your staff. You don't have to recalibrate the machines. You don't got to spend money. You don't have to do anything because as far as you can tell, the null hypothesis is correct. I'm not going to reject it. Everything's fine and dandy. Now, you're wrong, and that's a problem. You made an error. But let's think of the alternative. The null hypothesis is correct. Everything's working as intended. It's the right size. Everything is beautiful. And then you come along and say, whoops, no, this is bad. Let's change everything. Let's recalibrate. Let's spend money on training. Let's do this. Let's do that. Oh, Cynthia, someone's got it. Wonderful, yes. So type 1 errors in general are worse than type 2 errors. Now, of course, there's always going to be specific situations where personally you'd prefer to have a type 2 error. That's true. That's always going to happen. But as a general rule, type 1 errors are worse. In fact, alpha, the significance level that we've been talking about, is just the probability of making a type 1 error. That is what the significance level is. It's the probability of making a type 1 error. Why? Well, let's think about it. Here's my bell curve. Here's my assumed mean. Let's say 0, for example, if the null hypothesis is correct. Well, if I make a type 1 error, that means the null hypothesis is correct. You can't make a type 1 error if it's not. Do you agree? Right, it's right here. Null hypothesis is true, which means my bell curve is centered correctly. If I reject the null hypothesis, that means I must get a result that's off on the wing, whatever, if we do the same example as before, right? H0 mu is equal to 0, H1 mu is greater than 0. So if I reject the null hypothesis, I must fall in there. Well, what is the probability of falling in this rejection region? What is the likelihood that I fall in this rejection region? Well, 5%, or in general, it's just alpha, right? Whatever your alpha is. So alpha being the significance level is the probability of making a type 1 error. If I make a type 2 error, this is a little tougher now. If I make a type 2 error, that means the null hypothesis is false, right? Well, if the null hypothesis is false, then what is mu? If it's not 0, what is it? Well, it could be anything. Right? So I'm going to get a different value for the probability of making a type 2 error for every possible alternative. So the probability of making a type 2 error depends on what mu really is. So it's different for each specific alternative. Do we have something else that's different for each specific alternative? Is there something that's different for each specific alternative?
You mean comparing to the null hypothesis?
Yeah. I mean, in general, I mean, you have the null hypothesis, and then you have the alternative hypothesis, and you have lots of different alternatives. So what is something that we actually talked about today that's different for each alternative? Not the mean, no, that's not what we used. Not the probability, we called it something else. It did begin with the letter P, but it wasn't that. The power. Remember how we define the power of a test against a specific alternative. Against a specific alternative. The power of the test against a specific alternative. So the power for a specific alpha, for a specific mu not equal to 0 is the probability of rejecting the null hypothesis if mu has that specific value. Now remind me, what was the probability of a type 2 error? For a specific alternative? Is the probability of type 2 error, oh, that means not rejecting the null hypothesis, of not rejecting null hypothesis if mu has that specific value. So how are these two things related?
It depends if it's true or not, if U has that specific value.
Say again?
It depends if it's true or not, if U has that specific value.
No, actually, it doesn't matter. If you actually look at those, look at those two, look what I have written down. Look at this here. I was trying to color here. Let's do this one. Look at this here. And look at this here. And tell me what the relationship is between those. the probability of rejecting H naught if it has that specific value, the probability of not rejecting H naught if it has that specific value. There's a deep connection between them. Anyone see it? Well, yes, I mean, that's the given, right? It has that specific value. But the question is, what's the numerical relationship between these two probabilities? The probability of rejecting H naught given that condition and not rejecting H naught given that condition. They add to what number? They will always add to the same number. When I add numerically those two values, I will always get the same number. What is that number? And why?
Is it 0?
Well, those are both probabilities, correct? Probabilities can't be negative, right? So how will they add to 0? But they do always add to 1. Why do they always add to 1? Why do they add to 1? Is it just because you're looking for a nice number or because you understand why?
Because underneath the curve, it equals 1.
Even without a curve, it's more basic than that. These two probabilities are for exact opposite scenarios. Either we reject or we don't reject. Is there any other option? Either you roll a 5 or you don't roll a 5. Either it's heads or it's not heads. Two competing possibilities must always add to 1 because there's no other option. Either we reject or we don't reject. It's the entire sample space. Does that make sense? The probability of heads plus the probability of not heads is 1. The probability of evens plus not evens is 1. The probability of having a boy or not having a boy is 1. Ace of hearts or not having the ace of hearts is 1. Rejecting, not rejecting is 1. It always has to be 1 because they are competing and mutually exclusive and exhaustive. There's no other option. So this guy here, the probability of not rejecting the null hypothesis, sorry, the probability of rejecting the null hypothesis, this guy here has a name. This one here is called, we know this one here is called the power. The one on top is called the power, and the one on bottom is called beta. We have alpha, now we have beta. So the power plus beta is always equal to 1. The probability of not rejecting the null hypothesis, if mu has that specific value, is beta. The probability of rejecting the null hypothesis, if it has that specific value, is the power. The power plus beta always equals 1. Again, according to the syllabus, it says specifically, teach them conceptually, but don't worry about doing specific problems. I just want you to understand conceptually what's going on here. Okay? Does that make sense? Or a little sense, hopefully? Even if it's not like internalized, does it at least give you a basic idea? I hope so. I hope so. I hope so. Okay. So I'm looking at the syllabus here. And today, which was October 21st, it was to finish chapter 8 and to do part of chapter 20. So the next section is going to be chapter 20. I'm just going to start it a little bit. We're going to end a little early today because chapter 20 I usually do very quickly, and I anticipate being able to do the whole thing next time. So we'll just start chapter 20 in the book. Okay. So chapter 20 is inference about a population mean. Inference about a population mean. Now, when we did confidence intervals and we did hypothesis testing, we did both in the context of a population mean. But in those examples, we only did it for a very specific scenario, which was when sigma was known. In this chapter, we're soon going to be doing it when sigma is not known. But first, some conditions. Conditions for inference about a mean. Conditions for inference about a mean. Number one, data must come from an SRS. It has to come from a simple random sample. Number two, population must have normal distribution. Or at least be symmetric with a single peak. If it's not normal, at least be in the right ballpark. If sigma is known, then confidence interval is x bar minus z star sigma over the square root of n to x bar plus z star sigma over the square root of n. Right? We did that before. So now, what if sigma is not known? What do we do if we don't know sigma? Well, if we don't know sigma, how exactly are you going to use sigma in your formula for the confidence interval? Spoiler alert, we don't. What we do approximates sigma with what?
Is it with T?
Not with T. I know what you're thinking, but we're going to approximate Z with T. Right now, the question is, what do we approximate sigma with? Sigma is the population standard deviation. I do not know the population standard deviation, so I will approximate it with, so someone guess the mean. The mean is not the best approximation of the population standard deviation, because the mean is just the average. Some deviation is more of a spread. No, and it's just the sample size. The sample size, again, doesn't approximate the spread. It just tells us how large the sample is. There is something about the sample that should be a pretty good approximation of the population standard deviation. Again, okay, it's a good guess, 5-number summary, but again, not neg. We need one number, not Z. Oh, so Cynthia, the closest yet. She said the variance. The variance would be pretty good, but unfortunately the variance is not the right unit. We need something with the appropriate units. It is the sample standard deviation. Yes, Nikki, the sample standard deviation. And we had a symbol for the sample standard deviation. What was that symbol? What letter do we use for the sample? S. We are going to approximate sigma, the population standard deviation, with S, the sample standard deviation. In so doing, we now have, leave a space because there's something else that we have to replace, but ooh, that works. I'll skip a line here for a second. Now we have x bar minus something s over the square root of n to x bar plus something s over the square root of n. And the question now becomes, what is that something that we're going to replace z star with? And the answer is approximate z star with t star. Now I know what you're thinking. What the hell is t star? That's a great question. So what I'm going to do here is I am going to share my screen for a second. So the t distribution looks very similar to the z distribution. And in fact, if you weren't really analyzing it too closely, you might even say it's a normal distribution. It's the z distribution, but it's not. It's not. It's a little different mathematically. It is lower, doesn't go as high, and it's got a little more spread. Okay, so if you said it was a bell curve, if you said it was normal, nobody would argue with you because it certainly looks that way. But for technical reasons, it's not. But what it is as follows. It's just a little spread out more than the z. Why? Because when you're forming your confidence interval and you say from here to here, you get a very specific value if you know sigma. But when you don't know sigma, you lose some precision because you're approximating sigma now, which means we want to make the interval a little bit wider to compensate for that uncertainty that you have in your value. So confidence intervals in general are going to be wider for situations when you don't know sigma and you have to approximate it with S, where we use T instead. Now on your calculator, if you look on your calculator and you look at the stat tests, you see that for every z test and for every z interval, there's a corresponding t test and a t interval. And the only difference between them is that your calculator knows to use t star instead of z star. If you didn't have that, you would need to go to a table. Now, I don't know if there's a link to the tables here, but what you can see here in the picture is that there's actually not just one t distribution. If you look here, the solid line here is the normal, and then you have two different t's that they give you. With 9 degrees of freedom, it's a little bit less, and with 2 degrees of freedom, it's more less, it's further away. It's more spread out, the fewer degrees of freedom you have. So how many degrees of freedom are we going to use for any one of our problems? The answer is easy. It's always going to be the sample size minus 1. Take the sample size and subtract 1, and that tells you how many degrees of freedom you have. The more degrees of freedom, the closer you are to z. Because essentially, the bigger your sample size, the less we care that you're approximating sigma with S. And therefore, it should get closer and closer to the true z, the more your sample, the larger that your sample size is. But for small sample sizes, it does make a difference. And what we're going to do next time, oh, here, table C in the back of the book. Let's see if we can click on it here. So look here, this is the table here in the back of the book. What we can see here is that we have the confidence level just like we had with Z. But now this row is all about degrees of freedom. So if I want 90% confidence with 10 degrees of freedom, my T star value would be 1.812. What was my T star? What was my Z star for 90%? I forgot. Someone remind me. What was my Z star for 90%?
1.645.
1.645. And notice what happens as my number of sample size or my degrees of freedom goes up. These numbers are getting smaller and smaller and smaller and smaller and smaller and smaller. And by the time I've reached 1,000, I'm at 1.646. And Z star, it's so nice, it gives me as well, is 1.645. So the fewer, but the smaller my sample size, the slightly wider that my interval is going to be, because my T stars numbers are always going to be bigger than my Z star numbers. But by the time you reach 1,000, it's really pretty much almost exactly the same. You can see here 0.001 off, 0.001, 0.001 the same, 0.001, 0.002. Here is 0.006, but even that's not that much. Does that all make sense, everyone? So next time, we will go into depth for actually how to go about solving for all of this stuff. And we're going to end a little bit earlier than here right now. I'll put up the homework for chapter 18, which we just finished. And we will start chapter 20 next time. Okay? All right, everyone. So I will see you guys all Tuesday. Have a great weekend and have it full of math studying. Go ahead, Cynthia.
Thank you. Have a good day.
You too. On the quiz. Yeah, you want to go over it? Okay, so let me load up the quiz here. That would be grade book. Oh yeah, go ahead. Yeah, go ahead. Share your screen. That's fine.
Professor, I have a question.
Yes, go ahead.
Did you get my direct message? I joined a little bit late. I was just letting you know.
Who is this?
It's Michael Arrington.
I didn't, but I will change it accordingly right now.
Okay, thank you.
Welcome. Okay, so hold on, I'm just changing this. Okay, he's here. Okay, go ahead.
Can you see my screen? Or?
Yeah, I can see it. Mhm.
Okay. So it was just oh, this one right here. I was confused why, because I put 2.2, but it's saying it's the normal center.
Let's take a look. Researchers doing a study comparing time spent on them. Okay, so 200 students. In the sample, they spent an average of 2.3 hours per day and an average of 1.8 hours per day on studying and media. Okay, studying. Okay, fine. If all of the students, in fact, spend 2.2 hours a day on studying with a standard deviation of 2 hours, the shape of the sampling distribution of the sample average time spent studying is certainly going to be normal. And it is centered at 2.2 because that, oh, I see. So remember the central limit theorem?
Yeah.
What did the central limit theorem say? The central limit theorem said that if the sample size gets large enough, that it's going to look normal, correct?
Mm-hmm.
But how do I phrase this? If it comes from a population that's normal, it will be normal no matter the sample size. But if the underlying population is not itself normal, then the sampling distribution will not be normal unless the sample is large enough.
Okay.
Okay, now in our case, it's 200 students.
hmm
200 students is large enough for it to be normal. So are you saying that's, so the answer should be normal centered at 2.2 because
Yeah,
200
I
students is
put
large
the-
enough.
Mhm.
Huh?
Yeah, I put this one the normally distributed, but I guess it was just at 2.2.
Yeah, because if the sample size is large enough, then it'll certainly be normal.
Mhm.
And 200, remember we did the applet and like by 10, everything was normal?
Yeah.
So by 200, it's certainly going to be normal.
Okay, that makes sense. Thank you.
You're welcome.
And then, I was so mad. This one I knew, and I just pressed the
Oh, no,
time was
sorry
running
about
out, and like 10 ran out, and I was like,
Sorry
no,
about that.
okay, but that was the only one. How do I exit out?
Okay.
Thank you.
You're welcome. Any of you else have a question?
Professor,
Yeah.
it is a bit ironic that I actually have to ask you this again, but
Yeah.
I do appreciate you, I guess, you know, extending the homework when I asked you to do it, but I had been trying to do chapter 15 and 16 for around like 3 days, but I had some health issues that were preventing me from
Okay.
focusing and just doing them.
Okay, that's fine. Just do me a favor. Send me an email so I have it written down,
Mhm.
and I'll open up what you need. Okay.
All right, thank you so much.
I hope everything's better. Okay.
It is. Thank you so much.
Okay. Okay. Bye.
Bye.
All right, Bailey. Okay. So we were doing okay, so you want to share your screen again? All right, let's take a look what's happening here. So consider the circuit shown in the figure. The capacitor is charged to Q naught when switch is open. And it starts to discharge when we close the switch. Fine, okay. So the question is, what is the value of Q naught if right after the switch is closed, the current through R2 is 0? So let's do what we were going to do before. And let's assign currents everywhere. So I1 will
Wait,
be.
sorry, I was muted, but I had a question.
Yeah, go ahead.
I don't understand how it's charging because like it's not connected.
No, it's saying, you're the one who told me before. It was charged prior to this problem starting.
Oh, okay.
And then, and it was charged when the switch was open. And now we attach it to the circuit, we close the switch, and things start to happen.
Okay.
Okay, so I'm going to close the switch at time t is equal to 0. So the first thing I have is that I1 is equal to I3, because remember I2 is 0.
So it's not equal to I. Oh, wait. Wait, what?
I did I1 on the left, I2 in the middle, I3 on the right.
Oh, wait, okay, let me try redrawing it. Like,
Well, here, let me take a picture of the question. So you don't got to keep sharing. Okay, so go ahead, unshare, I'll share mine. Oh, I have
so
to
basically you could say the middle part just doesn't exist.
essentially.
Okay, I get it.
Okay,
Mm-hmm.
so we have I1 equals I3. And then let's take a look. Let's do a loop here on the right. We have E minus I1 R1 is equal to 0.
Wait, equal to 0.
Yeah, full loop is equal to 0.
What loop are you doing? Oh, you're doing that.
Why not?
Why are you doing that one?
Because,
Nothing goes through there.
well, I1, you got a battery. What do you mean nothing goes through there?
Because the I2 is 0. So it's like open.
I know, but that's why I have a wonderful connection between
Oh, I get it.
I1 and R1, right?
I get it.
And then if I do the other loop, I'm gonna start here in the top left. So I'm gonna first, I move across the capacitor, I gain potential because I'm going from low negative to positive.
Uh-huh.
So C equals Q, so Q naught over C minus I3 R3 is also equal to 0.
Okay.
And this tells me, by the way, that I3 is Q naught over C R3, right?
Yes.
And I3 is also equal to I1. So as a result, E, well, actually, I don't care about that. So now, so I get I3. So therefore, the current Q naught is equal to C R3 I3. Agreed?
Yeah.
Which is equal to C R3 I1, which is equal to C R3 E over R1, or C E R3 over R1.
Okay.
Do you agree with that?
Yeah.
Now B,
That's, that
right?
was easier than it felt.
Okay, so if Q naught has the value found in A, what is the current through R3 before the switch is closed, right after the switch is closed, and a long time after the switch is closed? Well, before the switch is closed,
Just 0, right?
it's 0 because you have no circuit for it to go through. Right?
Yeah.
Right after, well, we just solved for I3. Right after it's just I3.
Yeah. But I think we need I3 in terms of this stuff.
Well, I3 is Q
Oh wait,
naught.
no.
It's just E over R1.
Because the C you don't matter, right?
Well, if we,
Because it's like a wire, like a short circuit.
yeah, but we have this formula here, right?
Mhm.
So just plug in Q naught into there and everything cancels but E over R1,
Okay.
right? And long after.
Isn't it
So,
also 0 again?
well,
Because the capacitor becomes like an open switch.
yeah, so long after the capacitor becomes full, right?
Yeah.
And once the capacitor becomes full, there's no current anymore.
Yeah, it acts like an open switch.
Right?
Yep.
So now if Q naught has a value found in A, what is the current through R1 before the switch is closed? Well, before the switch is closed, then we just get E over R1.
Yeah, that's easy.
Actually, no, we don't.
What?
No, we
Why
don't.
not?
Because before the switch is closed, if you look at that circuit, there's current through there's current I2.
Yeah, but that's the same.
It's not
I want.
0. It's not 0. Oh,
Yeah, but it's in series.
Yeah, but the resistance is add.
Oh, right.
All right, so before it's E over R1 plus R2.
Yeah.
Right after it's 0. No, right after it's not 0. Right after it's the same as I3, E over R1.
Well,
because the current through I2 is 0, so I1 has to equal I3.
so is it not are we not using what we did in A?
We are. I1 is equal to
But in
I3.
A it says R2 is 0. Oh wait, never mind. Yeah, because it's a
Not R2, right? I2 is 0.
yeah.
And long after, it's just
Then
back
it's
to what it's just back to what it was before.
No, it's 0 long after, isn't it?
No, it's not.
But it's an open circuit.
No, it's not. You still have this part.
But it said no current goes through there.
That's only right after, doesn't mean infinitely after.
Oh, okay. Okay,
That's it.
um,
So you want to go back to this one and finish it?
yeah, but I wanna see, because I don't think I get the right after for this, for C.
Why not?
Because why
Right after,
is
we
it
know-
not R3 as well?
well, right
R1 plus
after,
R3,
right after this condition is satisfied, I1 is equal to I3, right?
yeah,
So we already calculated what I3 was. It's right here.
What about the R1?
What about the R1? It's right in there. You over
I mean,
R1.
the R3.
I mean, R3 cancels. It's R3
Oh,
between
oh, I
those two
see.
just happens to
Okay,
cancel.
okay. Because of the math, it canceled.
Yeah.
Okay. Okay, okay, so then, yeah, we can finish the other one then.
All right. So I'm going to copy this.
I tried to finish it, I'm not completely sure. Oh, also, I did not get D in 3. I just realized that.
Okay. Well, hold on. So I'm going to rewrite this. So the top row is 1, -1, -1, 0, 0, 0, 0. Second row, I'm okay with. Third row, I'm okay with. I'm gonna put the last row next. And then 0, 1, 0, 0, 1, 0, E over R, 0, 0, 1, 0, 0, 3, E over R. Okay, so now I am going to, so this is my pivot for the first column. Everything else is 0, which is wonderful. My pivot for my second column. So that means the second row, I'm going to keep. But the first row, to get rid of that -1, I'm going to add them. 1 plus 0, -1 plus 1, -1 plus 0, 0 plus -1, 0 plus -1, 0 plus 0, 0 plus 0. Third row, I have a 0 there. I'm happy with that. I'm going to subtract 0 minus 0, 1 minus 1, 0 minus -1, -1 minus -1, -1 minus 0, 0, 0. 0 minus 0, 1 minus 1, 0 minus 0, 0 minus -1, 1 minus -1, 0 minus 0, and E over R minus 0. And the last one has a 0 there, so I'm happy. So first column, great. Second column, great. Now we move to the third column. So for the third row, 0, 0, 1, -1, 0, -1, and 0. That's great. Second row has a 0 there, so everything is great. First row has a 1. I'm going to add them. 1 plus 0, 0 plus 0, -1 plus 1, -2, -1, -1, 0. Fourth row subtract. 1, -1, 1, 0. Fifth row has a 0 there. And for the last one, subtract 0 minus 0, 0 minus 0, 1 minus 1, 0 minus -1, 0 minus 0, 3 minus -1, and E over R again. Ooh, the fourth row.
You messed up somewhere.
Hold on, the fourth row is not good. 0 minus 0, 0 minus 0, 1 minus 1, 0 minus 1, -1, 1, 0, like that.
Yeah.
Okay. Good, good, good. Now move to the fourth column. So for the fourth column, the fourth row is good. The fourth row is good. The one above it, add them. 0, 0, 1, 0, -1, 0, 0. Two above it, add them. 0, 1, 0, 0, -2, 1, 0. For the top row, I gotta multiply the fourth row by 2 and add them. So 1, 0, 0, 0. Times 2, -3 times 2, 1, 0. Subtract 0, 0, 0, 0, 3, -1 e over r. Subtract 0, 0, 0, 0, 1, 3 e over r. So now first one's good, second one's good, third one's good, fourth one's good. And I'm actually going to flip these two rows here. So 1, 3, 3, -1, 1, 3, 3, -1. And then, so we'll see what we have here. So the fifth row is good. 1, 0, 0, 0, 0, 1, 3, and e over r. Add it to the one above it, 0, 0, 0, 1, 0, 4, e over r. Add it to 2 above it, 0, 0, 1, 0, 0, 3, e over r. Multiply it by 2 and add it to the second row, 0, 1, 0, 0, 0, 7, 2 e over r. Multiply by 3 and add it to the first row, which is 9 e over r. And finally, multiply it by 3 and subtract the bottom row, 0, 0,
Wait,
0,
9.
0.
Isn't it 3?
3 times, oh yeah, 3, thank you. And then, so now we're subtracting 3 minus 3, 9 minus -1, and we get 2e over r. So then I'm going to divide the last row by 10. So 2 over 10, I get a 5 in the bottom, 5r. Like that, right?
Mhm.
Okay. So now I can work backwards. It was I1, I2, I3, I4, and I5. So I5 equals E over 5R.
Yep.
I4 plus 3E over 5R equals E over R, or 5E over 5R. So I4 equals 2E over 5R. I3 plus 4E over 5R equals E over R, which is 5E over 5R. So I3 equals E over 5R.
Nice. That's what you wanted.
Really?
Yeah, that's what I got.
That's what you got?
Yep.
Okay, well, I'll just finish it because OCD. I2 plus 3E over 5R equals 5E over 5R, so I2 equals 2E over 5R. I1 plus 7E over 5R equals 10E over 5R, so I1 equals 3E over 5R. And finally, we have the current plus 10E over 5R equals 15E over 5R. So the current must be 5E over R again. Okay, that was fun.
All right, so just D on this one. I
Okay.
got stuck on that one.
So what's this? Let's see, find the current through each resistor a long time after closing the switch.
I got that.
Well, are these numbers?
What?
Or the numbers that we just got, where are they from?
That's finding the current through R3.
A long time after it was closed, right?
Yeah.
Okay, so we just answered C.
Wait, what?
What we just got, these currents are a
But
long
mine
time.
were
Yeah.
in terms of I, so that's not good then.
No, yeah, mine are not. Mine are in terms of just E's and R's.
Okay. Let me change that then, because I equals E over R,
And I want to copy this.
and so that becomes 4E over 5R. Right? Wait, this. Let me see if this is going to be right. So,
So let's see.
Okay,
Let's see if it makes
mine
sense. So I have E
are not
over
the
R.
same.
Okay, 1 second. So I1 is 3E.
Oh,
over
wait, never mind.
R,
This is,
And
that's
two-
why. It's not the same. Because the first one was right after search closed. It's a long time after search closed.
Okay,
So they're not the same.
but what I did is correct, all right?
Yeah, well, you did correct, but it's not going to help with C.
It's not. Hold on a second. And
Because
I3,
C is right after.
hold on. I want to make sure this is right. So the E over R, and then it splits. I have 3E over R and 2E over 5R, which becomes E over R. And then that becomes 3E and 3E, which is good.
Hmm.
And then 2E plus E. This should be 3E. Where's my I5 not 3E?
Hmm. Because I5 is 3R. I mean, the R5 is 3R and the rest
Oh,
are
oh,
all R.
oh, that's right. That's right. That's right. But these current, no, but the current should still add to the right amount, though.
But you said 3E, and then times 3 times R, so they cancel. And it's E over 5R.
But I'm writing the currents down.
I know, but you have it in terms of R.
Doesn't make a difference. The sum of the currents has to work. The total current in has to equal the current out.
But you should have less current.
It makes no difference if it's less current. The total current should still add to the right amount.
Oh, wait, I get what you're saying. But it does.
It doesn't.
What's it missing?
Hold on, 3E over 5R. When I look at this current here, E over R,
Yeah,
it splits into this and this.
yes, that works.
3, and that adds to the right amount.
Hmm.
Now this 3 splits into 2 this way and 1 this way.
Yeah,
That
that's
adds to
right.
the right amounts. When I take the 2 that came here and I add it to the 1 that's there, that does not add to this amount.
Because that's a negative one.
No, they're all positive. I don't get any negative numbers.
No, because you're losing, because it's 2 going in, 1 coming out, and the other's 2 going out, 1 coming in.
You're not saying what I'm saying. Look, this original one here is E over R, right?
Yes,
When that current gets to this point here, we have 3E over R this way, and we have 2E over 5R this way.
yes,
Now that's fine. That's a total of 5E
Yes.
over 5R in. Okay, now at
Yeah.
this point here, I have this way, I have 2E over 5R this way,
yes,
and I have E over 5R this way, which works. 3E
Yeah.
over 5R in, 3E over 5R out.
yes,
Now, when these come together at this point here, coming down, it should be E over 5R and 2E over 5R for a total of 3E over 5R. But
yes.
I'm getting E over 5R.
Yeah, because it's 3E over 15R.
No, it's the currents.
No, I know, but you're not taking into account the R.
I don't have to. I have the value of the currents. Current in equals current out.
Yeah, current in equals current out. but
And
it
it's not,
doesn't-
I'm not getting that. The
Mm,
current in is this number and this number. They don't add to this number.
Hmm.
Which means there's a mistake. Trust me, there's a mistake. Listen, it's a lot of intricate math.
okay,
Okay. So when you go over it, look for that error because it's,
Yeah.
I went quick. So
okay,
the final question is, what's the final charge in the capacitor? Okay.
yeah, but I think you need C for that.
Well, it'll certainly play a role.
I did C, just by the way.
You what?
I did C, by the way, if that is important.
And you got all the values?
Yeah,
So what's, well, okay, so well, this is easy then. What's I1?
I1 is 4I over 5.
What's
And then
I?
if I is E over R, so it would be 4E over 5R.
And what's I2?
E over 5R.
And what's I3?
0.
Okay, great. So let's do the loop. Negative I1R minus I3R3, which is 0, minus Q over C plus I2R has to equal 0.
Oh, that's it?
The loop.
Oh, right, because the V is the same as QC. Q over C. I mean.
And then just solve for Q.
Okay, so then it's just 4E over 5R times R minus Q over C plus E over 5R times R to 0. So that's the same as 4E minus Q over C plus E over 5 equals 0. And so that's Q equals CE. Does that make sense?
So let's take a look. So negative 4E over 5 minus Q over C plus E over 5 is equal to 0. So Q over C equals negative.
Oh, wait. I messed up. Okay, hold on. So that's negative Q over C equals 3E over 5. So it's Q equals negative 3EC over 5.
And okay. But why negative?
Because you have the negative Q.
No, it doesn't make any sense. Q is a positive number. There's just a math error somewhere.
Wait,
I mean-
what equation do we do to find this?
Well, it's Kirchhoff's law. It's just a loop.
But which loop did we use? I mean?
The top loop
Okay, so
or the
there's
bottom loop.
negative
Use whatever loop you want.
plus. Okay. Okay, so why is it negative? That's kind of weird. Q has to be positive.
Q is the magnitude of the charge. So yes.
Okay.
So listen,
Hmm.
it's obvious the strategy is fine, but there's a lot of intricate math there.
Okay.
So a one little minor mistake could throw everything off. So when you redo it and you rewrite it, just go through to be careful about it.
Okay. I will
Okay.
check. Yeah.
Okay. All right. Fine. So just tell your mom 35 more if that's okay.
All right.
And yeah, good times. Okay. I'm glad we had this talk.
Yep.
But it makes sense what we're talking about, right?
Yeah, I get like the concept more on this, I think, than like the earlier stuff.
Okay, good. Okay.
Okay.
All right then. All right. I'll catch you later, okay?
I
Okay, bye.